Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Looking at virtual work for this particular problem where we are given the potential function. We want to determine the stability, okay, as well as the equilibrium position, as well as the stability for the position. All right, 2 theta, 12 sine 2 theta plus 15 cos theta. Joe. Now, to solve the problem, to determine the equilibrium position, we'll take the first derivative of this function and equate it to zero, as well as uh, solve the resulting equation to determine equilibrium positions. And for the stability, we'll take the second derivative and plug in the equilibrium position to determine the stability. All right. So that for the equilibrium positions, as we said, for the equilibrium position, okay, we are going to take the V the theta is going to give us equal to set it to zero, and to do this we are going to have it to be 24 cos 24 cos theta cos 2 theta, okay, minus 15 sine theta, okay, all right, which we can set to zero. Now remember that cos 2 theta is same thing as 1 minus 2 sine square theta. So if we plug that in, we are going to have this to be 48 sine squared theta plus 15 sine theta minus 24. So we put it to zero. So if we solve this, we are going to arrive at theta, okay, to be equal to 30, 34.6 when positive, okay, 34.6 degree. Then to get the other angle, the other position, is going to give us equal to 180 degrees minus 34.6 degree, so which is equal to 145.4 degrees. 45.4 degrees. Okay. All right. Having done this, we can now go to determine the stability. As we said earlier on, determine the stability for each of the positions determined that we've gotten. So to do that, we'll take the second derivative. So if we take the squared V, okay, is we are going to have it to be minus 48 minus 48 sine 2 theta sine 2 theta. Okay, sine 2 theta. So that we'll have that. And minus 15 cos theta. Okay, so when theta is equal to 34.6 degree, 34, so we can determine the program for this position. So it's going to give us the squared v when we plug in this into what we got from the second derivative. Is going to give us minus 57.23, and you can see that this is clearly less than 0, so that tells you that it's unstable. Unstable, so the equilibrium is unstable. Okay, all right, so we can also do this for when theta is equal to 145.4 degrees. Okay, we'll see that what we'll have for this. So if we do this, we are going to arrive at plug in theta that into that equation here, second derivative. We are going to arrive at 57.22. You can see that this is clearly greater than 0. So the equilibrium here for this position is stable one. Okay, so these are the equilibrium positions and their stabilities.